Hi class, we continue our study in chapter 2 by moving into section 2.4. And section 2.4 is about something new, something called biconditional statements. All right, and we'll talk about the definitions of that. So our objectives in this section, the first one is to write and understand what we call biconditional statements. And the second thing we want to do is identify and understand good definitions. All right, so let's start with what a biconditional statement is. A biconditional statement is equivalent to writing a conditional statement. Remember, a conditional statement is if P, then Q. All right, so P implies Q. So it's equivalent to writing a conditional statement and its converse. And the converse is you flip P and Q. So for biconditional statements, we use the phrase if and only if. So it's really like two statements rolled into one. All right, so let's do an example of writing a biconditional statement. So write the given biconditional statement as both its conditional statement and its converse. So two angles are supplementary if and only if. So that's the biconditional. The sum of their measure is 180 degrees. So what I'm saying is this biconditional statement is the two statements, conditional statements, and its converse rolled up in one. So the conditional statement from this, if two angles are supplementary, then the sum of their measure is 180. Right? That's a true statement. Okay, right? That's just the conditional statement. Now let's look at the converse. So remember, the converse flips this. So if the sum of the measures of two angles is 180 degrees, then the angles are supplementary. Also true. So a biconditional statement just takes those the conditional and the converse, which are both true statements, and rolls it up into one. All right, the notation for this. So we use the notation that looks like a double arrows. This means if and only if. So thus, if you have P double arrow Q, all right, this is read as P if and only if Q. Right, that's a biconditional statement right there. That's what that means. P if and only if Q. All right, let's do some more examples. So a true conditional statement is given. Right, so if a closed figure is a triangle, then it has three sides. So I got three parts. Write the converse of the conditional statement. Decide whether the converse statement is true or false. And if the converse statement is true, write a true biconditional statement. If the converse statement is false, give a counter. All right, so the converse of this, remember the converse flips this. So if a closed figure has three sides, then it is a triangle. All right, that's the flip. Decide whether that converse statement is true or false. Well, that converse statement is true, as this sketch reminds us. As long as it has three closed sides, all right, it's going to be a triangle. So if the converse statement is true, which we just saw, write a true biconditional statement, right? If the converse statement is false, which we didn't see, we don't have to give the counterexample. So the biconditional statement is a closed figure is a triangle if and only if it has three sides. Right? That's that if and only if part right there. That's what signifies biconditional. All right, let's do another one. A true conditional statement is given here. All right? The true conditional statement is if x is equal to 5, then x squared equals 25. All right, so let's do the same things. Let's write the converse of the conditional statement, decide whether the converse statement is true or false, and then if the converse statement is true, write a true biconditional statement. If it's false, give a counter example. All right, first one, A here. If x squared is equal to 25, then x is equal to 5. Right? This converse is false. All right? The reason being it's false. All right? If that converse is false, all right, let's give a counterexample. For a counterexample, notice if x squared is equal to 25, then x may also be negative 5, since negative 5 squared is equal to 25. All right, let's talk about identifying good definitions. All right, which of the following is a good definition? So I've got three things, A, B, C, and D. A, a fish is an animal that swims. Rectangles have four corners. Giraffes are animals with very long necks. And a penny is a coin worth 1 cent. Let's start with the first one. Is this a good definition? Right? It's not reversible. Okay? So a whale is a counterexample. A whale is an animal that swims, but it is a mammal, not a fish. Right? So that's not a good definition because it is not reversible. It doesn't work in the other way. Rectangles have four corners. Right? Corners is not clearly defined. Thus, a corner does not necessarily mean 90 degrees, all right, as needed for a figure to be a rectangle. Right? So you could draw something that has four corners, That is not a rectangle. So that is not a good definition. Right? Giraffes are animals with very long necks. You can kind of see where this is going. Right? Very long is not precise. Also, choice C is not reversible because ostriches also have very long necks, but they're not giraffes. How about this one? A penny is a coin worth 1 cent. All right, choice D is a good definition. It's reversible, and all of the terms in the definition are clearly defined and precise. So you could say, if it is worth 1 cent, then it is a penny. That's reversible. All right, so our answer here is D, obviously. All right, let's do an example of writing a definition as a true biconditional. All right, so determine whether or not the following definition is a good one. To do so, attempt to write it as a true biconditional statement. So a right angle is an angle that measures 90 degrees. All right. So is the conditional true? If an angle is a right angle, then it measures 90 degrees. True. Let's see if the converse is true. All right. If an angle measures 90 degrees, then it is a right angle. That is also true. So since the conditional and converse are true, we can write a true biconditional statement here. Right? An angle is a right angle if and only if it measures 90 degrees.